Or would you? Yeah, you start. Okay. I'm trying to. Okay. Okay. Starting.
Yeah.
Welcome. Okay, hello, good evening, welcome everybody. Welcome to the Munich AI lecture by Professor Marc Toussaint from TU Berlin. My name is Michael Klimke. I'm the Managing Director of the Bavarian AI Agency, representing the Biosphere. Biosphere is the Bavarian network of artificial intelligence in research and application. It's a brand name. You may not have heard the name so far, but I can assure you that you are part of Biosphere already, in case you are a researcher in any AI related field. And the Biosphere is really a very renowned network consisting of over 40 universities in Bavaria that are doing research in AI. It's more than 800 professors. They and their groups are doing research in AI or with AI. It's 29 study programs in Bavaria. It's several doctoral programs. It's excellent extra-university research institutions such as Helmholtz AI, Fraunhofer Institute, DLR, Robotics Center in Oberpfaffenhofen. And of course, the whole network consists of many, many startups and small and medium-sized enterprises, research promotion agencies, and investors that make Bavaria successful in AI research and going to market also in application. The Bavarian AI Agency is entrusted with the promotion of this network and with the activation of this network. And that's the reason why we are here, why we are proud partners of MIRNI, of Professor Majid Kadif, in organizing the Munich AI lecture series. The aim of the series is to bring excellent people, even more excellent people to Munich and provide some exchange with you, the researchers, the students, and also to showcase what is going on in Munich and in AI. With that, I'm very happy to welcome you again. Have a great evening. Have a good conversation with Marc and with each other. And I hope to see you soon to the next upcoming Munich AI lectures. And please remember, Biosphere is your AI network here in Munich and in Bavaria. Thank you very much.
Great. Great, everybody. Thank you and welcome. So it's a great pleasure to have Marc Toussaint. Marc Toussaint is one of my favorite robotics researchers. So he has done very great work on task and motion planning for robotic systems. He's a professor at TU Berlin. Before that, he was a professor at Stuttgart University, and also a Max Planck Fellow. Also, he visited MIT, I think, for a few months or 1 year, right? So yeah, I don't wanna stop you. So please, Marc, you're looking forward.
Okay, hello. Thank you. So thanks for inviting me to this talk series. That's really an honor. And thanks, Majid, for the really high bar he used there for me to give the presentation. So I hope the sound is okay. Let me just quickly check if there is a notice from Zoom that I have to do something. No, then we just skip that. Okay, so today it's my pleasure to talk a bit about planning, but planning from the perspective of learning. And I want to start the talk with a little pitch and motivation. So let's say you are at some conference and you meet a person first time, elevator talk, and then you ask a person, what do you work on? And the person asks, I'm working on planning. And if you are at a robotics conference, then what do you think? How do you interpret that statement? Then typically you might think, oh, that person might work on path planning, RTs, probabilistic roadmaps, trajectory optimization, or maybe the person is more into control and is more about dynamic programming or something like that, robust control. Maybe it's also some person that works more on the logic level and it's about strips rules and logic planning and kind of, or maybe something in between, task and motion planning. That's all fine. But for the kind of gist of this talk, I want to highlight another way you could think about that. If somebody's saying, I'm interested in planning, like I'm actually interested in planning. So perhaps if somebody says that, maybe the point is much more that that person is actually interested in research to understand planned behavior. And by planned behavior, I mean behavior which is kind of goal directed, which means if the goal changes, then the behavior really has like drastic changes in the plan. So it could be like reactive goal directed, or it could be very long-term kind of organized behavior where there might be some long-term goals, and then if they change, then you have to show some other kind of behavior which takes completely different routes, or you have to do some plan switching, which also classical experiments in animal behavior can do. My point a bit is, and this is the gist or the background of this talk, is actually when people say, do you work on planning? No, I do work learning. Or people say learning, no, I don't do planning. I think that's not a good idea to like say that planning is opposing to learning. Also, we should, all of these people should be interested in trying to understand complex behavior and trying to understand planned behavior, no matter whether you do it with classical like optimization or search or learning methods. We should just try to understand that type of behavior. And this is what I'm interested in. And to make this more concrete, the outline of this talk is that in the first part of this talk, I will actually talk about planning methods mostly, and also highlight certain kinds of behaviors that I find interesting and what motivates me to actually work on these kind of methods. And then in the second part of that talk, more and more I will go into learning. And so the main topics actually will be this one here, which I will start in a second with, very reactive kind of controls. And then I will end up with some quite high level kind of work, which is the PalmE work with Google. And kind of in the middle, this will be very short sections for the sake of time. And now I have really under time pressure. I will keep these really brief and just advertise certain things and theory kind of we learned. Okay, so let me start with the first one. And I typically start with a little video. So here is a little video of behavior that is really simple. So there's much more complex stuff you can see out there in robotics research or so. And I'm just starting my talk, so I'm starting with something simple, but I want to highlight one thing, and this is what's happening right now. So what's happening right now is what you see is that I'm like changing the goal. And then let me go back. So I'm changing like this goal. And what you see here is that the system here is kind of like a boarding and approach direction. And if you think about this a bit more, I mean, this, the approach direction in also what I'm going to describe in a second is like 3 phases before. It's like 3 steps before reaching the goal. I didn't mention the goal. The goal of all of this is always the robot, pushes that little red box so that it ends up touching the green box. This is kind of like the overall task. But you see this like really kind of a reactive behavior where when the goal changes or goal constraints, I should say, change, then it propagates through this whole chain of intermediate like reactive controllers to show the behavior. I'm going to show a bit more complex behavior later, but let me like first try to explain what's happening. And first I'm going to explain it like in simple terms, and it is actually quite simple. And then I'm going to show you the math behind it also in a second. So a key thing in order to get this very reactive goal-directed behavior going is that the system maintains an estimate of these future states. So what does that mean? I mean, the system is right now in this state, x0, and that's the current configuration. And when I say configuration, I always mean the robot pose include and all the object configurations. So this is the current state, but the system will implement some kind of MPC method, MPC loop, which typically, estimates the horizon, like a half-second horizon of the next stage or so. But this one actually not only estimates a short horizon of the trajectory, but also some what I call keyframes or waypoints in the future. So for instance, at any point in time, it also estimates what is the pose when I will actually approach the thing, what is the pose when I will touch the red block, what is the pose when the red block will eventually touch the green block. And the MPC method will couple the estimate of all of these states so that whenever I'm changing a goal constraint, it immediately propagates back to the kind of MPC that I have to control now. And this is kind of what is behind the method. The motivation for this, it seems pretty basic what I'm showing, right? But the motivation for doing that research is that I felt, at least in my lab, I think also others, we need a more consistent control framework for task and motion planning. So I've done some work on task motion planning, we'll show some also later, but I always felt that we have some nice math and algorithms to write down the planning problems, but then some awkward gap to actually demonstrate it and translate it to robotics. And here is another example for like some really interesting goal-directed behavior. And basically, I'm wondering if I would have to, and you know, Boston Dynamics is not publishing how they did it. I actually wonder. And if they talk about it, they talk about sequence of funnels and I don't know what. But it was kind of interesting, like how I would write down a controller to realize these kind of things. And that's what the method that I'm going to present is. And yeah, so this is sec MPC or sequence through a given sequence of constraints. So in a bit more detail, there is a couple of control theory people here. They can digest also a bit more like the technical background. So the problem here is eventually formulated that we want to control the system to go through a sequence of constraints. Here, what I mean by constraints is that we have waypoint constraints. So these are those here. And they, when I say constraint, I typically mean an equality or inequality constraint on the configuration. And so when we're going to have to go through these waypoints, then, well, we have to fulfill these constraints. And then there's running constraints between them. And this is what I call here. And by the way, the sequence of constraints, this is what I consider to be the output of task planning in a sense. So it's the sequence of modes that I want to go through in that kind of thing. And also as a little comment, whenever I write inequalities here, they could also be equalities. We treat them differently, but for the sake of notation, inequalities, equalities, same thing for the notation. And so the full problem, if you would write it down like full, like jointly, what we really want to optimize is this mathematical program here. For those that are not into robotics or control, this looks maybe a bit overwhelming, but it's actually, for those familiar in control, it's really very standard. You have some control costs. That's basically the energy minimization or how smooth the trajectory is. You have some timing. So this is actually optimal timing control. You have some starting constraints, also end constraints. And then here you have this sequence of constraints. So the waypoint constraints at every waypoint and the running constraints between waypoints. So really a pretty standard way to formalize the problem. If you try to naively like let in like a standard NLP solver so run on that, it's not very efficient. And so to get this into an MPC cycle, model predictive control, you break that problem down. And in every cycle, you reactively only estimate first the waypoints. So that's just a much smaller problem, estimating what will it look like when I will start touching the cube and so forth. And then a very interesting timing optimization problem. In this work, first time, I really worked on timing optimal control, and it was really interesting, but I don't go into much more details. And then much more conventionally, a short horizon, 1/2 second smooth trajectory problem. Okay. That is now small enough or decomposed enough, that problem, that I can cycle it with 10 Hertz, and that's why it was so reactive, what you just saw. There's one thing I didn't really explain. When you saw this little video, maybe it looked like, you know, the robot is pushing again, and maybe you thought, maybe the guy implemented a for loop or so, right? Or a finite state machine, pushing, releasing, pushing, releasing. No, not at all. Actually, this behavior that you saw, that is like looping, this pushing, is implicit in that mathematical formulation, because there is one thing I didn't explain, is whenever it loses a control constraints, then it's actually backtracking into the previous continuous thing. And that's it. And that leads to this kind of behavior. Let me show a bit more longer this one. I mean, you've seen that one. And again, this looping here is the whole sequence, by the way, the full I don't know, in total it was 2 minutes. It's just running that same controller. There was no for loop or any outer kind of like loop or something like that. You've seen this, you've seen this. We can also mess around with the robot a bit more and try to, you know, play with it or make it annoy or so, and it just executes that sequence of constraints MPC. You can also do this for other tasks like stacking blocks. So this is a little stacking. It's very simple again in the beginning, and then I can just annoy the robot and play all kinds of tricks. And all of this is just this block of controller running without any weird software engineering around it or so, right? Okay, so Yeah, in terms of a control framework, I was kind of like happy with that. Let me just show a master student build on that. I'm, for the sake of time, not going to like give too many details of that. It's very similar to what I showed. Basically, there's one step more you can do, which is task switching. And here is what I would like you to look at. If you like focus on the top right video here, the goal here is for the red block to end up at this little red dot there. And there's one more step now. It's not only backtracking if something awkward happens, but it's also switching plans. So initially the robot thought, yeah, I can do it. But then the student kind of interfered and it had to completely switch plan. Instead of grasping it, it first had to grasp the tool and then pull through it, right? Oh, and that was another, let me back here. The goal is for the red block to end up at the red dot. It's hidden here behind the thing. And initially the robot thought, yeah, I can do this. It estimated all of the waypoints and it directly started, you know, going for it. And then the student interferes and well, okay, the plan is kind of like messed up. And then it kind of switches to another plan. That was not very nice control. But it switches to another plan and then to reach the same kind of goal. Okay. I don't maybe give more details about that. It's very similar to having a sequence of constraints, but now you also, the task planner gives you not only one possible sequence of constraints, but many alternatives of sequence of constraints. And you use this MPC estimates of feasibility of waypoints to switch plans. Pretty straightforward. I skip related work and want to like conclude with that first part with a couple of things. First, these behaviors that you just saw, I kind of like find them interesting and really think it's worth to think about what is the minimalistic mathematical formulation or problem formulation that you can actually, you know, understand these kind of behaviors, achieve them. Also, what I kind of like about this work, people sometimes talk about the sim to real gap, right? Meaning that the simulation doesn't match the real world. So I sometimes also think about the math to real gap. Meaning, and it's half joke or so, but I talked about this to students also, meaning like you wrote down all the nice math, but the question is how much software engineering do you then put on top of that nice math to actually, you know, realize this on the real system. And I find it sometimes not nice if you have like, you know, do nice formal models and then you start using behavior trees or finite state machines or some like many other ROS, whatever offers ROS kind of machinery to then actually get this to show complex behavior. And I almost feel the reason is that there is something missing that we haven't like formalized it well enough. And that was one attempt to do that. What I also like about this, that the formalism, the formalization really blends between optimal control and the way we formalize task and motion planning problems, and therefore, you know, tries to unite these two fields. Okay. So far, this was pretty basic and simple behavior. Now, let me switch a bit to more complicated behavior and also more, maybe more advanced work in particular on the problem of planning and understanding like planning problems a bit more deeply. And as I mentioned in this second part, I mean, all three of these topics are big topics, and all three of them are actually related to PhD students that I'm going to highlight because they're like heroes. They did like really great things. I just handed in the thesis a couple of months ago. All three of them at the same time. Yeah, but I'm going to keep it a bit shorter. So just to get an idea of what kind of now problems we talk about. So task and motion planning in particular tries to solve pretty, I don't know, a complex kind of planning problems and kind of behaviors. And these are, I tried to take different examples from different labs. So this is a classic one with Emo Todorov kind of being the lead maybe, and Igor Mordac being the first author of that, which is this contact invariant optimization, which is this morning I also talked about that, which I think demonstrates really amazing behavior. And just to be clear, maybe there are some people here that only are used to learning methods or so. It's generating all of these behaviors not at all based on data. There was no data, no learning, no demonstration or anything like that. This kind of behaviors are generated just from first principles. So you just write down optimization problems by specifying the physics and specifying the possible interaction possibilities. And then it comes up with these behaviors just from first principles in a sense. There is some own work that we did. By the way, here the goal is always to reach for the red ball, and it kind of comes up with all kinds of, and this is the only thing, you specify physics, and the goal touch the red ball, and then it comes up with all kinds of strategies actually to reach the red ball. And then this is like some work from MIT people, which is Piddlestream, Garrett, and then yeah, people from MIT. And this is also own work that I'm going to mention a bit later, which tries to scale to many, like coordination of many robots with different robots and scaling up. This one also, like, it's actually amazing that you see these behaviors just emerge from solving like a first principles optimization problem. Okay, so I think task and motion planning tries to understand these kind of behaviors, and I'm always saying understanding instead of just solving, because it really tries, you know, to describe these behaviors and ask what kind of methods, or what does it take actually to generate these behaviors. And one particular approach that I've been starting with was to formulate these behaviors as a mathematical program, as an optimization problem. And here's that optimization problem. We just gave it a name, logic geometric program, because it kind of mixes both logic variables, so really first order logic variables, discrete decisions, as well as continuous decision variables. And you also see this here if you look at these decision variables of the mathematical program. So these are just continuous variables, which are the configurations as we had in the control framework before. But here we have one thing more that we want to optimize over, which is the discrete decisions over modes, and that's what we called it. And these are really logic variables in that formulation. Many things are very similar to the control framework that we had before. And again, I mean, equalities, inequalities, same thing for the notation here. But basically, what this relies on is that we have models of these constraints. So models about what does it take to go from one mode to the other mode, and also what is the constraints that we have in certain modes. So one mode could be, for instance, like an object flying or something, and then you could say, what does it take for that thing to fly, and then you also can release it or so. So in principle, these functions here, they describe correct physics. And I'll talk about this a lot more later, but in many of the works, we coded these, or we just implemented them ourselves, implementing correct physics. Whereas this one here essentially describes all possible sequences of going through these physical modes. Okay, now in this first little part, I wanted to highlight, so we went in different directions from this kind of work. One, I think, was like a direction that I found was really interesting, was to try to understand these problems much better, because this one here looks like a innocent, small little mathematical program, but it really doesn't show the actual complexity. And so with one of my PhD students, actually, we started trying to understand the structure of these optimization problems much better by thinking of them as being factored mathematical programs. So for those of you that know machine learning, maybe you know factor graphs, Bayesian networks, things like that. So you don't describe a probability distribution just as one function, but instead you think of it as being many variables and coupling factors between all of these variables. And that leads to all kinds of insights of doing message passing, doing more local operations, understanding the structure of that distribution much better. Same actually for mathematical programs. What we optimize over is many variables, like the pose of the robot one time slice, pose of the robot another time slice, the relative pose of the object to the hand in one time slice, which is the grasp transformation. I forgot what the other variables are. You can just decompose the state space into the state of that object, the robot, the relative pose, all kinds of things. And all of the constraints actually are not just, you know, attached to all variables, but they're very local, just as in factor graphs. So all the constraints here are very local and just coupled to some of these factor graphs. And that alone, I think, is a very interesting and rich like representation of what the problem, the structure of the problem really is. And so we did some more basic like research trying to exploit that. And I'm not, because I could talk to each of them like for a longer time, but I'm gonna like go through all of these like 3-4 publications and just mention, you know, the gist of that. The first one is in many of these task and motion planning problems, we always have the back and forth between trying different discrete decisions and then solving the continuous mathematical program conditional to the discrete decision. So one operation that we want to do like really fast is to figure out when a mathematical program is infeasible. That's like crucial. The quicker you can say mathematical program is infeasible, the quicker you can move on and try like another discrete decision. And actually, this factored representation allows you, if a mathematical program is infeasible, to actually explain why it is infeasible. And explaining here means to figure out exactly the minimal set of variables and constraints that render this mathematical program infeasible. And we literally formulate that as a minimal set, like finding the minimal violation of violated constraints, which explain why that mathematical program is infeasible. And that's cool because if you understood this in one mathematical program, you can rule out all other mathematical programs that would have that same thing. In simple terms, if in one mathematical program it's completely infeasible to grasp that object, then maybe the same constraints appear in many, many other also mathematical programs, and they all will be infeasible. And you can just prune out huge parts of the search space. So that was one work. This is the thing here. There is more. Maybe I'll skip the second one and go directly to the next one. You can also, instead of analytically trying to understand when mathematical programs are infeasible, you can learn to predict the feasibility of a mathematical program. Now that's really interesting because now from all the mathematical programs that relate to different discrete decisions, you can, with a learning method, like really quickly evaluate which one is likely to be solvable. And you can not only do that based on that structure, but also conditional to an image. So for instance, you can give a neural network as an input this structure, and that's obviously a graph neural network, and an image, and then ask the network, so given this scene represented by the image, and this structural graph of dependencies and optimization variables and factors, do you believe it's going to be feasible? And then predict some probability of it being feasible. And if you have enough data, this heuristic becomes so strong that just by looking into a scene, it can immediately tell you which kind of manipulations are feasible in the scene. And that allows you to do search much, much, much faster than if you naively just search for all of kind of things. And then there was like this fourth one is also some fundamental work about unifying sample-based, optimization-based methods. I'll maybe skip that part for the sake of time, because I want to have enough time also about the learning methods. So all of this actually is work by Kim, who now went to New York after just handing in his thesis in November, December, something like that. Yeah, I'm just advertising that thesis, so please go ahead, read his work. I think it's really going deep into understanding the structure and complexity of these problems. Now, let me move on a bit, being even a bit more quicker about that one. We also did some work about scaling these kind of problems to very large fleets of robots that assemble constructions. That was actually in collaboration with architects from Stuttgart. It's really good, like architects actually also a whole cluster in CDC about architectural construction. And well, the architect said, can your robots, assemble large structures? And we initially said yes, and then later learned how hard it is, kind of like that. But we developed a couple of methods. So what is saw here are just different kind of buildings or structures that are being built. It's actually these here. And I think the first example is an example where there's heterogeneous robots. So some of them are mobiles, and then there is a crane, and then the crane can hand over some pieces to the mobile robots. And some of them, let me just skip on. This one is an example where we have many agents, like 12 or so. And I'll explain the problems in a second, but I mean, these are many robots and they all they always stand in the way. That's kind of like the problem. So really coordinating them to not stand in the way and allowing you to have this coordinate assembly is like really a challenge. This is another structure. And the last example is trying, we go here. Yeah, assembling like a piece, it's pavilion, I think you say, some artistic kind of structure from the architects in Stuttgart, which has quite so many pieces, 113. Yeah, and the basic question is, I mean, we wrote down this fancy mathematical program, LGP, which kind of claims to solve everything. Really, right? You can use it as a formalization of the problems, but can you actually then also solve these kind of problems? And if yes, how? And obviously, you cannot anymore jointly solve this holistic joint optimization problem over all agents over the full horizon. That's just insane. That's not possible. At least you can write it down on paper. That's good already, but not solving it. And so that student actually worked a lot on like decomposed methods to solve it. I skip over this actually quite a bit, but it's like it turned out that the core challenge was actually, well, the first insight is you definitely have to decompose the problem. It just doesn't work anymore that you plan jointly for all of them for all times. It just doesn't work. So you decompose. So far, so obvious. You like solve for one of the agents. But what I underestimated, I must say, is as soon as you decompose the problem, then actually it leads to so many follow-up problems, such as solving for one agent, you have a completely dynamic collision environment because all the other agents are moving. And then when you solve for agents separately, then you also have to like do the task, like coordinate them later. So have some coordination stage that kind of says which kind of task which agent does. Okay, so again, I want to highlight that thesis Valentin Hartmann also just finished that was digging really deep into that and developed basically strategies for decomposing the problem and coordinating the partial solutions to become big plans more reactively. Okay, which leads me to now go more into the learning topic. And I'm going to talk about this one a bit more. So the first thing is what I've shown so far was that was like really planning methods, right? So where some people would say, oh, you're just doing planning. And I remember also giving talks and then people, you know, asked about task motion planning. And they eventually also said, but all of what you're doing, that's not going to work. It's a dead end. And why is it obviously a dead end? Well, because it requires a model of the environment. And that's true. What I showed so far, it requires like mesh models of the objects and kinematic models of the robots, just requires full information about everything. And, you know, people would say, well, I mean, where are you going? This is a dead end, basically. This assuming full information, full model. But if you think about it, okay, and there is now two branches from that, either to fight back, and I'm going to talk about this fighting back now a bit, and the other branch is to say, okay, maybe it's a dead end, and then I'm going to do something completely different, which is more the large language models kind of approach. But to fight back, actually, these kind of methods, if you think about like closely, what do you really need? You don't necessarily need a perfect mesh model of the environment or whatever, even kinematics model or dynamics model. What you need is you still want to like formulate a mathematical program. To do that, you need a well-defined decision space. That's already some assumption, but that's kind of like clear. You need to know if you want to write down a mathematical program, what's the decision space? So what are the degrees of freedom, including also of the environment? And the other thing is you need these constraints. But these constraints doesn't have to be model-based, and these constraints can be learned. And that's a huge, you know, agenda in a sense, like a whole research agenda to then say, okay, let me try to learn these constraints. And I can learn them also like image conditional. So instead of like writing down a constraint, what it means to have a stable grasp, I can just learn a constraint to say what is, you know, the constraint of a stable grasp based on an image or like a depth camera or something. And the gist of this part of the work actually then is to say that we can still like formulate mathematical programs and also solve these mathematical programs. Also, if these constraints maybe are based on the neural descriptor fields or nerve representations or objects or scientific functions, and you know the word we used is pixel-line implicit functional objects. I'm going to explain in a second. And basically, you know, have image-based neural implementations of these constraints for the tasks and the dynamics. But the rest, I mean, the solver itself remains, but just the models, the constraints become learned. Okay, so we had a series of works of that. I just picked two, and gonna want to go a bit more also into technical detail again, and just describe how we actually set up the problem of learning such kinds of constraints. So eventually what you want is a system which takes a couple of camera images. So we need multiple here, let's say 2 at least, maybe 4 was better. And then from these camera image, or I should say conditional to these camera images, implement a function over configuration space such that this function is nice and differentiable, and I can use this function within an NLP solver to find points where this function is 0. So I want to learn a function such that if that function is 0 or smaller equals 0, but here 0, the constraint is fulfilled, and it's also nice and smooth that I can use it within optimization. And so the way we set this up as a learning problem, and it's related also to how MIT did it, kind of, but a bit different and so forth. But eventually the thing is that we represent the environment not as objects, but as fields, and it's a standard approach. So you think of this thing not as a mesh, but actually a field, a function over 3-dimensional space. It could be a scalar function like the sign distance function, but typically it's some feature function, high dimensional. I actually forgot, maybe we did 5 or 7-dimensional feature function that you use to represent this object. And this feature function is represented by neural networks. I don't go into the details. So this is this feature function over 3-dimensional space. And based on that feature function now, you can then train any kind of constraint that represents success of a manipulation by mapping samples of these feature values to the prediction of success. Right? So you then train like another, like it's kind of like task-specific network that can predict the success of some manipulation in a differential manner with respect to X, based on probing this feature field, this field representation on different key points. Okay, here is a little demo of that. Let me just open it like that again. And what we learned here is actually 2 constraints. The one which represents success of grasping a mug, and the other one which represents success of hanging a mug. Okay, so both of them are like not easy to code, or they're definitely annoying to code by code. Yeah, but you can, if you collect enough data, and we actually collected the data in simulation, you can, learn such kind of constraint function. And what you see here is really that it's using the neurally learned constraint function within an NLP solver to generate these kind of paths, and then end up like hanging in the mug. Okay. So that was about learning task constraints, but we also had some work about learning like physics constraints or like dynamics constraints. And I want to go really quick with that one also. When you want to model something like pushing, the success of pushing or the effect of pushing or some kind of other interactions, you actually want to have constraints that represent correct physics in your planning method. And how could you do that possibly without having shape representations or mesh representations? The same actually thing again, you train a neural system basically to implement the constraint function, which is 0 if it's correct constraint, if it's correct physics. So you actually have a discriminative function or a discriminative model of correct physics. Technically, how we did this is in the first stage, quite similar to what I just described. First thing is that you represent the environment not as like meshes and explicit shapes or something, but as a field, some kind of feature field over 3-dimensional space. Now what we did a bit different is that we also, for every object separately, so we assume to have mass of these objects, actually trained a latent state encoding. Latent state encoding means that we compress this kind of full field into a very low dimensional number. I mean, low dimensional meaning 13 dimensional or so. So you represent this by 13 numbers. Oh, the full state, also the position, orientation, everything, by 13 numbers. And to pre-train these numbers, oh, no, actually in this case, to actually find the latent code, it's actually determined that this code needs to be sufficient to decode a nerve renderer of this object. Right? So you can actually train a latent code of an object by requiring that the latent code is sufficient to render it again as a nerve. Okay, so we have a latent code, and then after we have latent codes, including also the position of the object, we can learn like a graph neural network or train a graph neural network to predict how that object or how the objects are interacting. which means, literally it's taking the state of the scene in terms of latent code of object 1, latent code of object 2, latent code of object 3, including also their poses, and then takes the graph neural network and then asks what's the dynamics, what's going to happen in the next time step. For those of you that know like similar kind of work, like visual foresight is an example, or other kinds of vision-based forward simulation or vision-based prediction of physics is kind of analogous to this kind of work. Okay, let me show you like a demo of that. First thing is I'm going to skip again to showing you the prediction part. Yeah, maybe a bit more in front. Okay, so if you focus, sure, on this one here, what you're going to see in a second might look quite a bit like a physical simulator. But what you see here is not really a simulation. It's a pure, like autonomous, like self-contained forward prediction of the states without any, further alignment with the world. So what you see here is purely generated by the graph neural network. Not only the state actually is generated by the graph neural network, also the rendering. So basically that full image here is just the forward unrolling of a predictive model, including also the rendering, which is by nerve decoding of the latent codes. So all of what you see here is a, completely neurally generated video with what we learned, which demonstrates forward simulation of the physics. And I hope you agree that this looks like a physical simulator. And if it looks like, that's good, right? Because that's great. And what is surprising is that it's pretty stable. That this completely neural learned trained system to predict the future is really quite stable. Funny enough, the color prediction is not so stable, but you even see it's also predicting colors. But here it's not like stably predicting that blue remains blue, but otherwise. And this is not so, it's not so easy to get such a stable, completely neurally learned, like forward simulator, like implemented. So this is what we did, and especially here on the right side. Can I do this again? Yeah, what you see here on the right actually that's a simulator which is useless for planning. If this is the kind of forward predictions you do, you cannot plan with that. But this is the typical kind of visual foresight, also predictions that you do, which are not stable over time, and you cannot do long-term planning with them. Okay, so we can also use this for planning with like forward simulating, or do I find this? Yeah, deformable objects. So this forward, forward simulation, this neural, let's say, forward prediction also works for deformable objects. And then you can use this also for planning. I'm not sure where I find this. Maybe, yeah, I'm not sure if I find this somewhere. But anyway, it's not surprising here, for instance, when we have such a stable long-term forward predictive model, neural model learned, then we can also use it for planning. Okay, let me stop this and conclude that part. So the point here is that this formulation of task and motion planning as a mathematical program being model-based, you might think is completely blocker to communicate with deep learning, to integrate learning methods and so. But I think it's not. It's actually, there is very clear and interesting ways to include very strong learning techniques within that whole framework. And the key thing is that the optimization-based reasoning methods, so the planning methods, basically they operate on neurally learned constraints. That's kind of the thing. Maybe I advertise it, of course, quite a bit. There's also like really limitations. So some of these models, they're actually class specific. Like the grasping was only for cups. I kind of hate that. And some other things here, like still limited that, we learn the constraints within the domain of the data set, but it doesn't really generalize to all kinds of objects and all kinds of interactions. So still many open problems, of course. And I want to advertise like the last PhD student, Danny Dries, who's now with Google DeepMind in California, and he did like large parts of that kind of learning to integrate learning into task and motion planning, as well as the talk, like the work that I'm going to talk about next in this talk. Okay, so let's switch a bit like the approach and be a bit more mainstream in a sense, and talk about large language models. So we had this joint work, PalmE, which raised quite some attention. It's now my most cited paper, which I find awkward. I worked so much on so many like great work, right? And then this is like this little paper, and within like half a year, it was like my most cited paper, which is interesting. Anyway, so what's that? So the basic question was, what can LLMs do for robotic manipulation, large language models? And like everybody was asking that question around the time. When was it? A year or a year and a half ago or something like that. And we talked with people from Google, in particular Pete Florence, but also many others at Google, Andy Zhang and many others, Carol Hausmann. Well, and there was us, meaning Danny and me, and we had expertise on TAMP, and in particular also ideas about what we think is interesting behavior. And again, interesting behavior would be kind of planned behavior that really is goal-directed and switches drastically if the goals change. And then Google, of course, there's expertise on large language models, especially Palm is a large language model. And so we kind of came together and wrote that paper, which is also the basis now for RT2 and other follow-up kind of things. And yeah, let me explain. Let me first show videos first. Maybe I'll start them all at the same time. So the first one here is classic one. You have an LLM, and there's all kinds of prompt, which I'm going to explain in a second. And then the end of the prompt is that it gets in a language input, bring me the rice chips from the drawer, and then it's doing this. And it's also reactive, because this is also the LLM replanning is iterated in some kind of cycle. I forgot the cycle, but maybe with 2 hertz or something like that. Not quite 10. I don't know. It's just repeated replanning if there's some intervention, and then it can just bring the rice chips from the drawer and bring it somewhere. And this is a similar thing, bring me the green star. And I flipped the subtitles here. So this one is pushing something to the turtle, all the green stuff to the turtle, and push all the red stuff to the coffee mug. And it's, it does it. How does it work? In a nutshell, it's a large language model. It's pre-trained. I'm going to explain in a second, but it's special in the sense that it not only takes language as input, but also images and segmentations, also state vectors of robots. So it allows as inputs not only words, but other stuff. And so it's really a multimodal, like sequence or transformer model. And it's trained, among other things, but it's trained eventually, the fine tuning eventually is then trained to predict action plans as an output. So in a bit more detail, actually, so this is like a typical image, transformer image. These are the input tokens, and you have, typical words. Usually every word translates to token, but as you know, from vision transformers, for instance, like an image translates to what I forgot how many tokens. So we can, in the input sentence at arbitrary places, basically put also other stuff than words, like given this image, how can I grasp the blue block? And then let it predict only words. It's only outputting words, actually. And so the input actually interleaves words, images, vectors, and so, and that's what we call multimodal. It's all of them are like embedded into tokens, but the way they are embedded in tokens is quite different. Sometimes we use vision transformer to embed images, other kinds of similar ways to embed segmentations. I'm going to explain in a second. Also, yeah, and the encoding, the token encoding is then pre-trained, typically with nerves or other kind of techniques in here. The output sequences, maybe that's I'm going to ask most, are actually action primitives that were previously trained in a prior work. So they're fixed. Also something I don't like so much about the paper. But some like grasp yellow block is literally, has to be parsable, and it's literally then translated to existing action primitives. Here's more examples. I don't know if, but these are literal ones. Given image, how to grasp the green block. Answer, first grasp the orange object and place it on the table, then grasp the green object. Why is that? Because the orange was on the green, actually, in that image. A given image, how to stack white object on top of red object. Answer, first grasp green object and place it on the table, then grasp white object and place it on the red one. So same thing again, the green one was kind of like blocking, and it understood from that image that it has to grasp the other thing first. Okay, I can, in a second, conclusion will be that it works. But then he also did a really good job that in the study to try to do some science, in a sense, to figure out what is actually, many ablation studies. And that is actually a really cool part of the paper. So because there's many possible data sets in which you could train, and many possible ways you could pre-train parts. So you can pre-train the large language model first just on many language, or also on visual question answering, and then like fine-tune it or fine-tune it directly. There's different ways to pre-train the encodings and then fix them, freeze them, or maybe also include them in the refinement. Many options of how you can do things. And that's very strong ablation studies you find in the paper. For the sake of time, I really have to hurry up. I'm going to skip over that. So all of these are basically ablation studies and basically showing positive transfer. It really shows that like a large language model that was trained on many different tasks, so on language prediction and visual question answering and different robotics tasks, then if you fine-tune it for one particular robotic task, also performs much better than if you would have trained it initially with just one robotics task. And there's a couple of examples like that, and also in comparison, freezing versus fine-tuning and item. Okay, I'll skip over that. So let me come to conclusion. So the first conclusion is that system-wise, the main effort was really engineering, I think. And the conclusion is that Danny is a hero in engineering, and that's why he got immediately hired by Google after that. So and the engineering really is in data handling and I don't know, training this, how much was it, 500 billion parameters kind of model, which required special software and system infrastructure. Also strong about the paper, I think, are all these ablation studies. Yes, so sorry about time, if you have to, if somebody has to run, that's fine. So all the many ablation studies, I think, also scientifically like really strong in the paper. But the eventual conclusion also of the paper is that eventually it works. And we expected that, right? Because, well, we put in tons and tons of data and you train it on data and it works. Which brings me to the last part of the talk, which is the it works discussion, which, yeah, I hope you have time. I can like it just a few moments, because maybe I find this most interesting. So the it works discussion. So it came to my mind in particular when I was sitting last November at Coral in the audience and looked at all the papers at the conference. And I was sitting in the audience, and basically there was one paper after the other, which says we collected all of this data, did some learning, imitation learning, and then it works. And there was like papers over papers over papers that do that. And it's, on the one hand, it's impressive, and then you also sit there and have to digest. Yeah, what's the open challenge, or what is the field then doing? Also at Coral, there was an early career panel discussion. And in one of the interesting questions there was to one of the members of the panel, so if you had a lot of if you had a lot of money, what would you invest it in to make progress in the field? And that person said, I would invest in more data. And there were a couple of questions like that. What if you would have, I don't know what, and the answer was always the same, I would invest in more data. And that person did not say would invest in more research or novel methods, or even not in institutes, building a new building, or investing in people, infrastructure, or in insights or research or anything. But the answer was, what would he invest in data, right? And that made me also think. And yeah. So, and this is the it works discussion. Maybe it's already clear where I'm getting at. So my point basically is, I think that might be right. If your goal is to get things to work, so if it works, it's like the only goal, then maybe that's right. You should just invest into more data and then invest in behavior cloning and cloning that data. And then you might end up with kind of like systems. And okay, so to kind of like keep it simple and to conclude that little discussion. So I think getting things to work is doing many good things for the field also. I mean, thanks to machine learning, imitation learning, and I'm putting imitation learning there in particular because I feel like half of the learning in robotics fields nowadays doing imitation learning, we are making great progress. And you saw all of these videos that in the media people get, ooh, this humanoid is folding clothes and is doing all kinds of things, right? Yeah, that's thanks to this, like mostly imitation learning, I would say. We also learn scientifically quite some things, especially initially, like we learn about diffusion and how good it is to represent multimodal distributions and transformers and scene representations, multimodal syntheses, and so. And also, I mean, the field becomes larger and pushes and makes more progress because companies have super strong incentives to get things to work. Right? They want to make the product and they invest so much, and that's also why companies are also strong in that. But I guess you might have, anticipated. My point is a bit that as a field, as a research field, I guess we could have broader goals. And my point is eventually like trying to understand the problems, because I feel the more we like push this thing of we have to get things to work, and the way you get them to work is to collect more data and use imitation learning, the less we actually learn about the problems itself. The problems of behaviors, for instance, plant behavior, right? And that's why I think it's cool, of course, also to do imitation learning and all of these things. But I think research should also try to understand the problems itself. And in that sense, I think it would be too narrow if the main scientific output of our field is we know how to clone behavior, to maybe put it like that. And I even have a fancy citation thing. So Feynman once said, "What I cannot build, I do not understand." And somehow in my head, I always thought this means when I build something, I understand it. But I think nowadays maybe this like logical conclusion is not really necessarily true, right? And also logically, this is not true. So building something that works doesn't necessarily mean understanding, and we should be aware of that. So understanding is maybe more than just getting things to work. Okay, so thanks for your attention. So these are the PhD students, first authors, and some collaborators. Yeah, thank you.
That's great. So I need to bring my logistic here.
Okay.
Any question? Yes.
Thank you for the very nice talk. It's very stimulating.
Mm-hmm.
The question is about the very first example you showed about the main cube and the red cube.
Mm-hmm.
You mentioned that there are no for loops and everything is limited.
Mm-hmm.
There was an example where one of the handled for the other one. That also.
Yes. I see that one where it was actually like really plan switching. Yeah, the word emergent is a bit in that case. So this second video where my student actually did more complicated things, and that was plan switching. The word emergent is like really an overstatement. So both of these methods, they always evaluate the current correctness of the constraint, the feasibility of the constraints, including those in the future. And that system was just running as it is, and it was evaluating the feasibility of the current plans and the current constraints. And as soon as it estimated those become infeasible, which is the direct grasping and placing, it switched to another plan. And that's what the system does, yeah, without any, other techniques in that. Is clear? Okay.
So before going to the next question, if people in Zoom also have questions, write it down. I can try to have a look there. Mm-hmm. Yes.
Yeah, great talk.
Thank you.
And I specifically like your conclusion. Palmi is really impressive. My question is, is it now really purely data-driven? Is it pure learning, or is there still some classical control model-based methods involved? If it's so, to what extent?
So the question maybe for those also in the Zoom is whether Palmi is purely data-driven or whether there's other classical methods involved. So first, the boring bits, there is definitely like classical methods involved in terms of the PD control of these primitives, and like how precisely even the learned action primitives, because the action primitives were learned, but still how they're like really controlled. There's always control theory on those level. There always is kind of. So that's an obvious part. And then there is another place where actually classical methods enter these, and I should have emphasized that. The system was trained on data, But in order to fine-tune it to actually predict plans, like real action plans, we trained it on data that were the solutions of our task and motion planner. That also was, initial reason why we thought we can play a role. So it was basically the classical model-based methods, our methods, that generated the data for that system to imitate. And that seems like a poor role initially. So you think we developed like decades of AI research, like classical AI research, to have planners, and then the only output of these planners is data for neural systems to imitate. It actually makes sense because the neural systems can imitate that kind of optimal planning behavior conditional to images or conditional to language input, which the classical solvers could not. So that's also, I think, a very strong role also for the classical solvers.
But this is already a huge role, right?
I think so too.
Yeah.
Because
so
you could argue.
The data, you need good data to learn, right? So
I agree. And also scientifically, you could argue that, I mean, it's of course not true that we understand machine learning, but let's assume that we understand, imitation learning or something like that. Yeah, then if you take that literally, then the actual scientific question becomes, where does the data come from? And how can we generate data that induces the right generalization that we want to have? And if you end up to say the answer is our classical reasoners, then I think that's true.
Yeah. But it's also, I think, another interesting way of combining symbolic methods.
Yes. Yeah, I agree. Yeah.
More question. Yes.
Thanks for the nice talk also. I'm from robotics. We build robots that navigate outdoors to pick trash. So we navigate in unstructured environments, and our planners still are, our planners are like almost all planners in the robotics community as of now, deterministic and analytical. And my question is, what would be your timeline for when at least a significant share of robots in production, not only research, would be to some extent learning based? And what can we expect then?
Tricky question. So I think if you don't need learning base, and maybe for trash collection, you could argue in which parts is so. I think the companies should also not, without thinking about it, to push too much to transition to a learning-based system. I'm also like cooperating with Amazon, and we had all of these things about picking objects or so, right? And many things are still engineered there, and I think that's also for a good reason very often, right? So, but if it's only like, and also I think in terms of the full system engineering, like the system as a whole, I think for a very long time, it will not be end-to-end learning of the whole system, but just some components of it will gradually become more learning based. And I think this is already like happening, that some components of that become more and more learning based. And for trash collection, it could also be, for instance, learning grasps, like for arbitrary from point clouds or something like that, because that's a very good component, and that you can collect data very well for that.
Yeah.
Yes.
Thank you for the talk. And I have a question. I see all of your work, most of your work, like in PC and LGT, constraint optimization based. But in motion time, the first step always do is like field exploration.
Yes.
Do you have any idea like how can you extend your method to cover this?
Yes. Great question. So it's great fun for me for years to think about sample-based versus like optimization-based methods, right? And I think I'm slowly making progress in my thinking, but I don't there's not much published. I think Kim also has a view on that. Interesting. So in these two things, like Kim had another perspective on that. So you can read about what Kim thinks about sample-based planning. So, yeah, I'm thinking a lot about that eventually. And I think, I mean, optimization-based methods are very efficient because in very high-dimensional spaces, they eventually just go downhill, which is like almost a one-dimensional problem to go downhill. That's why they scale so well. Sample-based methods, they have to explore so much, right? But I more and more think about that you can have much better sampling of local optima in NLPs, right? So, and if I manage, or if we manage in the team also to get these samplers of local optima and NLPs to be much more diverse, it's a bit like diverse NLP solving. where you don't want to have an NLP solver that just finds one solution, but a whole diversity of solutions. And I think there is ways to get there. And if we could get there, and these are sample-based methods, then this combines the best of these two worlds. And there is also, I can mention, there's related work like Stein variational approaches. I don't know if somebody knows Stein variational approaches, which also try to maintain a diverse set of particles to descend in an energy landscape for probabilistic inference, variational inference. And I'm thinking about like similar things for optimization, where you have like a whole family of particles descending in an NLP solver landscape, but ensuring diversity of all of these solutions. And I think if we get there, these kind of technologies, it's going to be like a really, I think, different also problem setting, right? And then like, that could combine both sampling and optimization. Mm-hmm. Yes? Hi.
When GPT came out, people immediately tried to break it.
Mm-hmm.
It's not jailbreak. So how do you break
I don't know if they have tested or so. That's a hard question. So I don't actually have data on that, right? So any answer I come up with now is a bit like improvised. So, but I think so. My gist would be, I think it's not hard at all to break it. So I think that it's going to be very easy. I mean, also here the kind of like, did I actually explain the prompt in all details? So the full prompt consists of the first half of the prompt, which is auto-generated. And this first half of the prompt is an auto-generated prompt, which is basically a scene description. And it's something like, here is an image of the scene. In the scene, you see a green object, which I call Peter. And there's another object called Jane or whatever. They can have names, they don't have to have names. Anyway, this first half of the prompt is auto-generated from code. And then the last half of the prompt is then the human prompt, the actual question or task. And I think it'd be super easy to let the human request to not match at all with the words and references that have been auto-generated in the first half and prompt them lost. Yeah.
Yes. It can be the last question.
Older works also on planning as inference.
Yeah.
And now recently this has been used quite a lot of models.
Yeah.
I was wondering, what is your thought on that?
Yeah, that's such a big question. So I also get sometimes asked this, sometimes people even frame the question, in the past you did all of this nice work on planning as inference. Why do you now do this boring optimization-based methods? There is a technical reason also why I actually at some point switched from probabilistic inference and graph models to optimizers, just because of the hard constraints and this whole like theory of Lagrangian methods and so, which is and still is unclear to me how you could have like similar methods actually in graph models or probabilistic inference. But and this goes back to the sampling-based question also. One real issue then, if you then go to just optimization methods and NLP solvers, is that you lose this diversity and the multimodality that you also get in diffusion process, right? And that my take on that is, yes, and there is now an obvious gap of how I could bring these very efficient and quite aggressive downhill optimizers and NLP solvers to also have diversity. And yes, I also believe that diffusion models also can be an answer of how you can generate that diversity that I earlier like described, that I want to have a diverse actually solutions to NLPs. But I haven't published on that. Don't do before me.
Okay, thank you very much, Mark, and thank you everybody. Yeah.
Thank you.